Okay, hi grade 12s. For this section, we're going to be looking at an electrochemical cell. So it leads us into the lab activity we're going to do in the following day. So hopefully you've already watched Tyler DeWitt's videos on electrochemistry. He does a really good job of introducing the concept where we're taking and converting chemical energy into electrical energy and vice versa, okay? And his second video there where he's showing the ions getting oxidized and reduced and the atoms getting oxidized and the ions getting reduced at each of the electrodes is a really good one. So I'm going to leave him to let him do all of the explaining. I'm just going to show you in our notes where that concept is shown. Okay, all right, so you're going to be working through pages 15 and 16. Again, this is our introduction to electrochemical cells, and in the next day you're going to be doing a lab activity based on this information. So this is just introductory to get us ready to see what it looks like, and I'll review it again tomorrow. Okay, so we're looking at an electrochemical cell where we have two parts, the anode and the cathode, and you want to remember that the anode is the site of oxidation and the cathode is the site of reduction. All right, in our lab we have these little porous cups. They're little ceramic cups that allow ions to move through them. They act the same way as the salt bridge does when you're looking at the electrochemical cell. So I'll just show you what that looks like in our diagram just to see the difference between the two. Okay, you're going to read through here, do some highlighting, and then we're going to be looking at the diagram on page number 16. So here we have our electrochemical cell, and let's just add to this diagram here anything else that we need to if you haven't already done this. Okay, so first of all, we do call this a voltaic cell, galvanic cell. That's the same thing. And from the cell notation, you can see that the zinc atoms go to ions. That means it's showing your oxidation that's taking place at the anode. And then the double lines represent the salt bridge. And then what's happening at the cathode, you're getting the reduction, the copper 2 plus ions going to copper. Okay, that's the diagram that's represented in this cell notation. So anode oxidation, then cathode reduction. So let's show what that looks like in the lab. Okay, so here I have my zinc. I've got a strip of zinc metal. It's in a solution that has zinc nitrate in it. Okay, this is the anode. This is where oxidation takes place, and you want to see that, right, the zinc atoms are going to zinc ions in the solution. At the same time, because it's oxidation, it's losing electrons. How many electrons? 2 electrons per every zinc. So do you see there how it's indicated that this is a representation for every atom that gets oxidized, 2 ions are lost. Those electrons are captured in this direction through the voltmeter, and they end up on the copper side. Copper is where the copper ions are getting reduced. So you can see here that they're in a solution of the copper nitrate, so copper 2 nitrate solution. Those ions are available, okay? They are getting reduced, and so it's the copper ions that are turning into copper atoms, okay? This electrode will actually start to get bigger. The mass will increase as that copper starts to build up. So that's, I could put it in a copper color if I had a brownie color, but you can see that. At the same time, my zinc electrode is losing mass because they're essentially turning into zinc ions. So the mass over here will start to go down. The mass of the cathode will start to go up. Okay, this was representing our aqueous solution. This represents our flow of electrons. And our salt bridge that's in our center of our electrochemical cell, as he explained in the video, that's just to balance out the ions. You want the electrons to keep flowing from the anode to the cathode, and so to prevent that charge buildup, the ions that are in this solution, the ammonium and the nitrate, will just flow in the direction that makes sense based on their charges. So if on the anode side, right, you can see that you have a buildup of a positive charge, does not it make sense that the negative ions will flow this way? No reaction taking place, just balancing out that charge so that you can keep the flow of electrons going. Look at it on the other side, on the cathode side. The copper ions are turning into copper atoms. So you've got less of a positive charge. You've got an imbalance in the nitrates that are in this solution. So the ammonium ions are going to flow in this direction. Again, it just balances out those charges so that the flow of electrons will continue to move. Okay, so what I want you to do is I want you to answer questions 1 and 2, and you can see down here you're going to just show what this looks like, except we don't have to set it up where we've got 2 beakers and a salt bridge going through. We can simply put a porous cup inside of the other solution, and it would show that the solution inside of my porous cup is my copper nitrate solution, right? Aqueous. That is going to be where I put the copper strip. So that's my site of reduction. That's my cathode. And then the solution that is on this side, and I'm not going to, it's not really yellow, but can you see how it's all the solution right here? This is the one that is my zinc nitrate. Okay, because it's where the zinc metal is being placed. Okay, so instead of separating out the electrochemical cell, we've just kind of snuck it together. But again, the notation for this cell shows that my zinc gets oxidized at the anode and my copper gets reduced at the cathode, and my double lines that represent the salt bridge really can also just show me that's where the porous cup is. There's a few more things you're going to add to this diagram, okay? You want to add on there the mass that goes up and down. You want to show where the electrons flow and in which direction and how many. And then you want to show the flow of the ions that are in the solution, okay? This is going to turn into something here. This is going to turn into something here. And then you're going to have a flow of ions. Something is going this way and something is going this way in order to charge out or balance out those charges. Okay? And if you flip back to the diagram that was on page number 10, this one shows it perfectly here with regards to aluminum in our aluminum nitrate solution, our copper in our copper nitrate solution. The direction of the electrons is going to be whichever has the strongest reducing agent capability is the metal that's going to get oxidized. So comparing these two, it actually shows you that it goes from the aluminum to the copper. It could very well go the other way around, but if you hook it up to the electrodes, you won't get that charge because the electrons aren't flowing in that direction. So you see where you need to understand which one's the strongest one to figure out the flow of the electrons, okay? Start off with this as an introduction, do the textbook reading, and then I will review this in the next day's lesson where we do another bit of a small dry lab where I give you some data. Okay, good luck.